discussion. In this lecture, we shall be talking about the architecture of ARM microcontroller, the third part of it. Now, in this lecture, we shall be mainly talking about the processor modes and registers in the ARM architecture. There are some special registers we shall be trying to tell you the necessity and roles of this special register, something about exception handling, and there is something called thumb mode of execution, also very briefly about that. So, again we shall not be going into very much detail of this, because this course is primarily meant for a hands on demonstration and training for designing embedded systems, but learning some basic concepts on the architectural issues will always help you in becoming a better designer. This is the main purpose of trying to give you with some of the initial backgrounds of the embedded system design and the architectural concepts. Okay? Fine. So, let us start with the processor modes. Now, in the ARM processor, during execution, at a given time the processor can be in one of 7 modes, and this table summarizes the 7 processor modes. The user mode is the normal mode during execution of a program. When a program is executed, normally we say that the system is in user mode. This user mode, the acronym is USR, we sometimes denoted by USR. This is the normal program execution mode. Now, you know, in processors we can have interrupts. From external devices some interrupt signal might come. If it comes, the program that was executing will be suspended. We will have to go to some interrupt handling routine, run that routine, and then again come back and resume the interrupted program. Now, in ARM, 2 different levels of interrupt processing are permissible or allowed. One is called high priority, other is called normal priority. Now, this FIQ is the high priority mode. This FIQ mode is entered when a high priority interrupt is activated and is acknowledged. Now, the point to note is that when a high priority interrupt is being processed, if some lower priority interrupt comes in the meantime, they will not be acknowledged, they will be ignored. So, higher priority interrupt will be having real higher priority over the lower priority ones, they will be handled first. And IRQ is the low priority or the normal priority interrupts. This IRQ is the processor mode, which is the mode, you see this FIQ and IRQ we are saying is the mode when the corresponding interrupt handler routine is executing. That interrupt has come, we are handling the interrupt. During that time we say that processor is in either FIQ mode or in IRQ mode. Okay? Well, there is a supervisory mode which most of the modern processors they have. There are some instructions like supervisory call, trap, these are or there is a instruction called SWI, software interrupt. There are various names to these interrupts, but the purpose of these instructions is that these instructions are some ways to transfer control to the operating system. Well, in a computer where there is an operating system, these instructions allow the processor mode to be changed from user mode to supervisory mode, and then just like a subroutine call, control will jump to the supervisor or the operating system, right. This is what is done here. Now, in the supervisory mode or SVC, this is as mentioned here a protected mode, and this mode is required only when there is an operating system in your implementation. Well, in all embedded system application you will not require this. but in system where there is really an operating system and you need some protection, you need to have this mode of execution. And abort is a mode, again this is an optional mode for cases where you want to have memory protection, like you want to see that when a program is executing you are supposed to access only this region of memory. If accidentally your program tries to access any memory location beyond the permissible limits, this abort interrupt will be generated and the corresponding processor mode is called the abort mode. For handling memory access violations, the processor goes to the abort mode, right. And undefined is actually something which is kept for future expansion. Well, some instruction opcodes have not been defined, they are undefined. So, if by mistake you are trying to execute an instruction whose opcode is undefined, you get an undefined interrupt and the processor mode goes to undefined state, UND. And there are instances where you want to run some privileged operating system tasks. For that you typically go to the system mode. The system mode and supervisory mode are very much related. So, I am not going into the detail of this, because for an embedded system design these are not really required. Very rarely you will be requiring these modes in an actual system implementation. Okay. So, ARM supports all these modes. So, ARM is quite flexible in terms of its architectural features. Talking of registers, ARM has a large set of general purpose registers, as I mentioned earlier. So, in total there are 37 registers. All of the registers are 32-bit long. Talking about dedicated registers, there are 7 registers which have specific purpose. One is the program counter, PC it is called. There is one which is called current program status register. Well, for those of you who are familiar with some microprocessors, some architecture like 8085 or any other microprocessor, you will be knowing that there is something called condition flags. Whenever some instructions are executed, these condition flags are set or reset. There is 0 flag, carry flag, overflow flag and so on. So, this CPSR or the current program status register is like a flag register. It consists of several flags which are set depending on the mode of the processor or the instruction execution, right. And there are 5 saved program status register. Now, this concept is interesting. There is one CPSR and there are several SPSRs, saved program status registers. You see, in a conventional processor, whenever an interrupt comes, what we do normally? We save all the registers in the stack. That can include also the status registers, the flags. Go to the interrupt handler, finish everything, come back, restore all registers and status register from the flag and resume execution. But in ARM, there is no support for stack. There is no instruction to push or pop instructions in stack or from stack. So, pushing and popping the status into stack you cannot do like that. Just for that reason, what is done? There is a special CPSR copies which are maintained. Suppose a program is running, current status is stored in CPSR, there is an interrupt that has come. So, the content of the CPSR will get copied into an SPSR, then interrupt handler will run. Before coming back, the content of the SPSR will be restored back into CPSR. So, it will be restored back. So, there is no stack as such. it is the user's responsibility to restore the value from the CPSR and then again move it back and forth, right. And of course, there are 30 general purpose registers. These are named typically R0 to R29. Okay. Fine. Now, depending on the processor mode, it depends how many of these registers you can actually access. Now, 16 registers are typically visible in a specific mode of operation. These 16 registers are as follows. There are 13 general purpose registers R0 to R12. Stack, there is no stack I told, but R13 is earmarked as the stack pointer. If you want to implement a stack yourself by software, you can use this R13 for the purpose. Okay. And R14 is a link register. You see, for subroutine call instructions, let us say for a conventional processor, the value of the program counter is also pushed in the stack, but here there is no stack. So, there is a special register called the link register. The value of the program counter gets copied into the link register whenever there is a subroutine call, and when you are returning back from the subroutine, whatever is there in the link register is copied back into program counter. So, you start from there again, right. And program counter is accessed as R15 and of course, current program status register. Now, here I shall show a picture later which will show you the different registers, how they are accessed in different modes. Now, in terms of the general purpose register where you are expected to store some data, I told you that registers are all 32 bits in size, but in terms of the operations which are supported, you can have 8-bit operations, 16-bit which are called half word operations, or full 32-bit word operations. So, in terms of the 32-bit word, the whole 32-bit is referred to as the word, and when you are using half word operations, the lower 16-bit is used. This is the half word, and for byte operations, the last 8 bits are used, right. So, you should remember this. When you are using a byte operation, the last 8 bits of the register will be used, and for half word, last 16 bits will be used. Okay. And these are not used for arithmetic operations, only for data transfer operations, because all arithmetic operations are only 32 bits in size, but when you are transferring data from one place to another, you can transfer 8 bits or 16 bits or 32 bits. From memory, you can transfer 8 bits of data into a register, it will go into the last 8 bits. Okay? Fine. Now, current program status CPSR. So, what does it contain? So, it contains, as I had said, the flags. So, what are the flags? There is a overflow flag denoted by V, there is a carry flag C, for subtract operation we call it the borrow, there is a 0 flag, it checks whether the result is 0 or non-zero, and the sign flag negative or positive, right. Now, in addition, the processor can be in many modes. Well, processor I said there are 7 modes, but to keep with future expansion, ARM keeps 5 bits to store mode. So, in 5 bits you can support up to 0 to 31, 32 modes can be supported maximum, and this bit number 5, 6 and 7, they are meant for thumb state, then 6 and 7 are for enabling and disabling the interrupts, the high priority interrupt and the normal priority interrupt. If these bits are set to 1, these are disabled, if they are 0, they are enabled. The other bits in between, they are normally not used, they are unused. Okay. Now, talking about the special register, just a relook again. This R15 is the program counter. So, as you know, so program counter always holds the address of the next instruction in memory to be executed, right. So, if the destination register is program counter, which means you are jumping to there. Okay. Link register R14 is earmarked as a link register for subroutine call instruction. Now, in ARM, the subroutine call instruction is called BL, branch and link. This BL stands for branch and link. Branch and link means, well, in the BL instruction you will be specifying the address where to branch. Before branching, the current value of the program counter will be saved into LR R14, and then the destination which is specified will be loaded into PC. So, that jump will take place, right. So, when you are coming back, the value of LR will be copied back into PC. So, you resume execution from where you left. And R13 is earmarked from stack. Of course, there is no stack in ARM, I told you, but it is reserved as a pointer. If you want to implement it in software, you can do it. And CPSR, as I told you, this holds the current status register with respect to the program that is being executed, and whenever some exception or interrupt comes, the CPSR gets copied into one of the special or saved program status registers, SPSRs. They will hold a copy of the CPSR. So, when you come back from the exception routine, that SPSR has to be copied back into CPSR before you resume execution. Okay? This is how they work. Now, talking about the program counter, there are two modes of execution. One is the ARM mode, one is the thumb mode. Let us make the distinction clear here. We first talk about the ARM mode of execution, which is the default mode of execution. ARM mode says that all instructions are 32-bit wide. They are 32-bit instructions and they are word aligned. Word aligned means all instructions must start from an address, memory address I mean, that is some multiple of 4. This is what you mean by word aligned. The need for doing this is that, well, again I am not going to detail of this. When you interface memory with the microcontroller or the processor, there is a concept called memory interleaving. If you have 4-way interleaving, then 4 consecutive bytes starting from an address which is a multiple of 4 can be transferred in a single clock cycle. But if it is not so, you will be requiring 2 clock cycles. So, your memory transfer will become slower. Just to have faster memory access, ARM insists on word alignment. Okay? And multiple of 4 means what? The last 2 bits are 0. So, any address with the last 2 bits 0 means it is a multiple of 4. Therefore, when it is in ARM mode, the program counter is expected to hold the address of an instruction, right. So, always the last 2 bits will be 0 of the program counter. So, the last 2 bits of the program counter are actually not used in the ARM mode, they will always be 0. Okay. So, this already you have mentioned, the PC can point to 8 bytes ahead or 12 bytes depending on the number of stages. But there is another mode of execution whenever you do not need the full power of 32-bit processing. Maybe you are using the ARM processor in a very simple application, where smaller instructions, 16-bit instructions are there, a subset, instruction subset. Here in the thumb mode, the instructions are 16-bit wide, that means 2 bytes, and they are half word aligned, means the instruction addresses are multiple of 2. So, earlier it was multiple of 4, it is multiple of 2. Multiple of 2 means the last bit of the address will be 0. So, in the program counter, the last bit is 0, which is not used, right. So, this is the main difference between the ARM mode and the thumb mode. ARM mode is a superset where all instruction encoding are 32 bits. Thumb mode is a subset of that, where you make all the instructions shorter, 16 bits, because of which maybe the total program memory will be required to be much smaller, your code density will be much higher. For small applications, you can have much cheaper mode of, you can say, means implementation, right. So, thumb mode is used for such cases where you need small systems. Now, this diagram gives you an overview about the registers in the different modes I told you. Well, in the user or the system mode, well, you have access, as you can see, to the 13 registers R0 to R13, then R13, 14, 15 SP, link and PC, and the CPSR. And the 5 SPSRs which are there, they correspond to the other 5 modes. If an interrupt FIQ comes, then CPSR gets copied into this SPSR, and this R0 to R7 will be there in FIQ, but the other registers will be specific to FIQ. So, if you come back, they will again change. And in IRQ, R0 to R12, the whole thing is there, only R13, R14 are specific to IRQ. SVC also, undif, abort also. So, this depends which are the registers which can be accessed when you are writing the interrupt handler. Like here, when you are writing the first interrupt handler, FIQ interrupt handler, you are allowed to use only the registers R0 to R7 in the user mode, and these are the specific registers which you can use. They will be automatically used in the FIQ mode, and they will not overwrite the original registers here, right. You need not have to save, restore them. There is another copy of those registers in the register bank. Okay, fine. Now, talking about the CPSR once more, this is again the picture of the CPSR I told earlier. The last mode, the 5 bits. Now, the specific bit combinations are showed here. For the 7 modes, the mode bit combinations are defined like this: 10000 means user mode, 1001 is FIQ mode, and so on. And condition code flag I already mentioned, negative 0, carry and overflow. And interrupt disable, if it is 1, the corresponding interrupts are disabled. And thumb mode, this bit indicates whether you are processing in the ARM mode or the thumb mode. If the bit is 0, then you are in ARM mode. If it is 1, you are in thumb mode. So, in this way, it is decided whether which mode of execution you are selecting, 32-bit mode or 16-bit mode. Okay. Now, talking about exception handling, there is a process like this here followed. There is an interrupt vector kind of a table. This is called a vector table. This vector table is present from address 0 onward. 0x00 means 0x means hexadecimal 00. These are hexadecimal numbers 00, 04, 08, 0c. So, each of these entries are 4 bytes long. This can be seen from the address. next one is 04, 08, 0C, 10 and so on. So, whenever any exception occurs, exception means interrupt, memory access violation, undefined instruction, all these are exceptions, some kind of interrupt, okay, or the supervisory call. So, whenever this happens, the CPSR will be copied into the corresponding SPSR. So, you know there are 5 SPSRs depending on the type of exception. CPSR will be copied to the corresponding saved program status register, and the corresponding bits of the CPSR will be set depending on which mode you are in. And during interrupt processing, the interrupt bits will be disabled, because if they are enabled, then another interrupt might come in between also. So, in order to avoid nested interrupt from coming, while you are doing the interrupt handling, interrupt bits can be disabled. Then before coming back, well, the return address will have to store in this LR register corresponding to that mode. You see there are separate LR registers for the different modes, and PC is loaded with the vector address. You jump to these. For return, the exception handler will do the reverse thing. So, it will be loading back that SPSR into CPSR, it will be copying to SPSR, and LR will be containing the return address, it will be transferring it to PC. Okay. So, it will be jumping back. Now, the point to note is that here the entries out here, these are not addresses of this interrupt handler, rather these are instructions. Typically, these are jump or call kind of instructions. So, when you come here reset, so there will be a jump from here to the routine which is handling reset. Well, if it is let us say this FIQ, so if you come to 1C, here there will be an instruction which will be jumping to the interrupt handler for FIQ, okay, and so on. So, these are all one word instructions that are stored in the vector table. These are not addresses of the routines which are stored, it is the actual instruction, some instruction that is stored here, right. Okay. So, this is what I have already mentioned. The vector table is stored from address 0x00 to 0x1c. So, one word allocated for every exception type, and as I had said, this word will contain some instruction, some branch instruction. Okay. It will branch to the corresponding interrupt handler. So, it does not contain any address, you should remember this. Okay. This already I have mentioned. So, talking about the ARM and thumb instruction set, a quick comparison. So, in ARM mode, the T bit in the CPSR is set to 0 and for thumb mode it is set to 1. The differences are as follows. Instruction size in ARM mode, there are 32 bit instructions. In thumb mode, as I said, there are 16 bit instructions. The number of main instructions are 58 and 30. Conditional execution, I told you, conditional execution is a feature where some instruction will be executed depending on some condition is true or false. So, in ARM, almost all the instructions support conditional execution, but in thumb only for branch instruction you can check for 0, non-zero, carry, no carry, but other instructions do not support conditional execution, just only the branch, just the normal case. Data processing instructions in ARM mode, it supports barrel shifting. Like I told you, when you add two numbers, you can say you add the second number shifted left by 10 positions. This will be done automatically by the barrel shifter, but in thumb such instructions are not there. Here there are separate shift instructions and there are separate ALU instructions. So, there is no single instruction that combines shifting and ALU adding together. Such instructions are not there in thumb. Program status register in ARM mode, you can do read write in privileged mode. but in thumb mode you cannot access those program status register, those are prevented from being accessed. And for registers, in ARM mode you can use the 15 GPR general purpose registers R0 to R14 and the PC, but in thumb you can use the 8 GPRs, 7 high registers and PC. So, high register means high order 16 bits of the registers. So, there are some specific registers which can be accessed. So, only a subset can be accessed here, that is what is meant. Conditional execution I told you, let me take an example here, we shall be discussing some more cases of conditional execution later. Conditional execution, it controls whether or not CPU will execute the current instruction. Now, most instruction in ARM, it allows a conditional attribute to be specified. Let me take an example, an instruction like this. Normally, if you do not use this EQ, just imagine this EQ is not there, then move R1 hash 0 means this R1 is initialized to 0, right. Now, if I give this move EQ, this means I am checking the 0 flag in the CPSR. It says if the 0 flag is set, which means equal condition is true, then only you do the move, otherwise you do not do the move. So, this instruction will be executed depending on certain condition. Okay. So, this is how the conditional executions execute. We shall see later that using this kind of conditional execution just allows us to prevent branch instructions in many cases. It makes the code density higher, less number of instructions. Okay. So, with this we stop with our brief discussion on the ARM architectures. From the next lecture onwards, we shall be moving on to some aspects about the ARM instruction sets and the other features about ARM, which will be helpful in the actual experimentation that we shall be showing you, we shall be giving you demonstrations on. And all the demonstrations that we shall be showing you would be based on some ARM boards, and also a few experiments we shall be showing you on the Arduino boards. Okay. This we shall be seeing over the next few weeks. Thank you.